In this video, I will show an example of how to use the substitution rule for definite integrals. In the previous two videos, I have already explained the theory behind the substitution rule, which is just the chain rule backwards, and I work out some examples, specifically these 4 examples. I'll put a link in the description. But all of these are examples of indefinite integrals, or simply antiderivatives if you prefer. In this video, I will use the substitution rule to compute a definite integral. This one. There are 2 approaches for this. One method is to first find an antiderivative. In this case, we could do a substitution, then integrate and undo the substitution. And once we have an antiderivative, evaluate it at x equals 2 minus evaluate it at x equals 1. Nothing surprising. This is entirely fine and it produces the right result. However, there is an alternative method which is a little bit faster. We can use the substitution rule directly in the definite integral. To do this, we need to use the substitution everywhere, the function, the differential, but also the endpoints. The advantage of this second method is that it saves a bit of time. We do not need to substitute, integrate, and undo the substitution. We can skip the undo the substitution part. Let's write down the details. I want to compute the integral from 1 to 2 of x times x squared plus 1 to the 100 with respect to x. This integral is asking us for the substitution u equals x squared plus 1. Why? Because the derivative is basically x up to a multiplying constant, which we already have here. Let's do it. I use the substitution u equals x squared plus 1. If I do that, I also need to change the differential. The u will be the derivative of x squared plus 1, which is 2x, times the x. Let's prep the integral. I need to separate 2x for the differential. And I have multiplied by 2, so I also divide by 2. Perfect. I have the piece I need for the differential now. So the integral becomes 1/2 the integral of u to the 100 du. However, I also need to change the ends of integration. 1 and 2 are values of x. When I perform a substitution, I need to substitute everything. So I need to change 1 and 2 into the corresponding values for u. When x equals 1, u equals 1 squared plus 1, which is 2. And when x equals 2, u equals 2 squared plus 1, which is 5. So my new integral goes from 2 to 5. Now that that is done, I can find an antiderivative for this function. It will be 1/2 of u to the 101 over 101. And I need to evaluate it at u equals 5 minus evaluate it at u equals 2. So I get 5 to the 101 minus 2 to the 101 over 202. And that is the final answer. That's it. As I said, I didn't need to undo the substitution at the end. Once I fully complete the substitution, I can finish the calculation from there entirely in terms of u without worrying about x again. To finish the video, let's write this up in the form of a nice little theorem. I am going to call it the chains of variable for definite integrals. Or if you prefer, the substitution rule for definite integrals or the backwards chain rule for definite integrals. Here is the substitution rule for indefinite integrals that we had already justified. When it is a definite integral instead, we also need to make sure to change the ends of integration. To make this into a theorem, I should introduce my variables and add some hypotheses. A and b are real numbers with a less than b, f and g are functions, g needs to be differentiable and the derivative must be continuous on the interval ab. As for f, it only needs to be continuous, but where? If we're going to compose f with g, I need the range of g over ab to be contained in the domain of f. This is just a technical way to say that I can write f of g of x for any x between a and b. And that's it. The proof follows immediately from the substitution rule for indefinite integrals, plus the fundamental theorem of calculus.